We turn next to composite functions. This is just a definition. We say that if f and g are functions, then f of g of x is a composite function, and we often use this notation here to denote that. I know it looks like the word fog, but what I'm writing is a little circle. So f with a little circle after it, and g of x is just means the same thing as f of g of x, and we say that the function is f composed with g. It's also important to note that the domain of the function, the domain of the function f of g is numbers x such that g of x is in the domain of f. It's kind of a mouthful, but it sort of makes sense because in order to get a value here, we have to plug in some value x, which means that it has to be in the domain of g. Then we're going to get a y value out of g, and we have to plug that back into x, which means that first of all, x has to be in the domain of g, and then whatever we get has to be in the domain of f. So both conditions have to be satisfied in order for a number x to be in the domain of f composed with g. Let's do just a quick example. If we let f of x equal excuse me, if we let f of x equal 1 plus sine x and g of x equal the square root of x, we can find f composed with g and g composed with f. And I just want to demonstrate to you that these are not the same thing. In this case, we have this is going to be f of g of x, which means first we're going to replace g of x with the square root of x. So this is going to be f of the square root of x, and now we go up to function f, and every place we see an x in that function, we replace it with the square root of x. So that's going to be 1 plus sine of the square root of x. On the other hand, if we do g composed with f, we get that's going to be g of f of x. So now f of x is equal to 1 plus sine x. So now when I go back to g, and every place I see an x in g, I replace it with what's inside these parentheses, and that gives us the square root of 1 plus sine x. So you can see that although those expressions look similar, they are clearly not the same thing. So the way we would say that in mathematics is we'd say that the composition operation does not commute. It's not like addition where a plus b equals b plus a. It's more like subtraction where depending on which order you do it in, you can get a different answer. It's worth noting that in addition to composite functions, we can also find sums, differences, products, and quotients of functions. Um, These are exactly what they sound like. This is simply when we take two functions and either add them, subtract them, multiply, or divide them. The important point here is that when you do that, what you do is you get a new function, and you can actually describe it by a name such as this. In other words, if I only know that two functions are f and g, the expression f plus g in parentheses is in fact the name of a new function, that is, its sum. I'll just do an example of that here. So if we start with the assumption that f of x equals x squared plus 2 and g of x equals the square root of x, then that means that f plus g of x is equal to uh, x squared plus 2 plus the square root of x. That's all you really have to say. This is in fact a new function whose name is parentheses f plus g, and the product function, we'll do it this way, is going to be x squared plus 2 times the square root of x. Don't really need parentheses there, but I do need them in the first case because I'm multiplying the entire function f by the square root of x. So this becomes now, we'll use the distributive property, x squared times x to the 1/2 is x to the 5/2 plus 2x to the 1/2. I could have written it as 2 square root of x. I just wanted to emphasize, I wanted to keep these in the same notation. If you wanted to, you could write it this way. You could write x squared root x plus 2 root x, and that would also be an equivalent answer.